జ్ఞానం మీ భవిష్యత్తును నిర్మిస్తుంది.
డిజిటల్ ప్రపంచంలో మీ విజయానికి మార్గదర్శి.
ఇక్కడ మీరు నేర్చుకుంటారు, ఎదుగుతారు.
Path with Ajay. Learn and grow and move forward.
You have 30 seconds to find the remainder of 3 to the 100th power divided by 7. Attempting manual multiplication, multiplying 3 by itself 100 times, is a mathematical dead end that guarantees a timed-out exam. Success in competitive quantitative sections relies on algorithmic pattern recognition rather than brute force arithmetic. Every number carries a predictable mathematical fingerprint, a recurring behavior that allows you to bypass the calculation entirely. To identify these fingerprints, we use 3 high-speed solving frameworks: divisibility rules, unit digit cycles, and the remainder theorem. Mastering these frameworks targets the specific properties found in approximately half of the quantitative section, reducing complex problems to sub-30-second operations. We start with the bedrock of number classification. A number system is a standardized, universal framework for representing values, categorized primarily into real and imaginary numbers. For competitive exams, focus exclusively on the real numbers branch. For these tests, you can proceed under the assumption that every number encountered is a real number. Within this system are prime numbers, values with only 2 factors, 1 and themselves. In this category, 2 is the only even prime, and the number 1 is excluded from the prime set. Divisibility rules function as high-speed sorting algorithms, allowing you to quickly verify properties to eliminate incorrect multiple-choice options. The rule for 9, for example, is verified by summing the individual digits. If that sum is divisible by 9, the original value is as well. To check divisibility for 11, we analyze the difference between sums of alternating positions. Using 1, 2, 3, 4, 5, 6 as an example, we sum 1, 3, and 5, the odd positions, and subtract the sum of 2, 4, and 6, the even positions. This yields 9 minus 12, or -3. Because -3 is not 0 or a multiple of 11, the entire number fails the divisibility check. This alternating sum method allows for the immediate rejection of incorrect options without the use of long division. When solving for massive exponents, the unit digit concept allows you to ignore the bulk of the calculation and focus strictly on the final trailing digit. This is the task: determine the final digit of 7 raised to the power of 45. Exponent outcomes follow strict repeating loops, known as modularity, a property where values wrap around a fixed cycle. The power cycle for 7 follows a 4-step wheel. 7 to the first ends in 7, squared ends in 9, cubed ends in 3, and the 4th power ends in 1. To find where our exponent falls, we divide 45 by the cycle length of 4. In modular systems, the quotient is irrelevant. Only the remainder, the leftover value, dictates the final position. A remainder of 1 maps directly to the first position on our cycle wheel, confirming that the unit digit is 7. This cyclic framework neutralizes the difficulty of large exponents by reducing them to a simple position on a loop. The remainder theorem extends this logic from unit digits to full division problems, isolating the exact leftover value of complex operations. Division is structured by a single formula. The dividend equals the divisor multiplied by the quotient plus the remainder. Consider the problem of dividing 7 to the power of 10 by 4. First, we reduce the base number. 7 divided by 4 leaves a remainder of 3, which we express in modular notation, a system for recording remainders, as 7 is congruent to 3 modulo 4. We then examine the powers of 3 to find the cycle. 3 squared is 9, which, when divided by 4, leaves a remainder of 1. Finding a remainder of 1 completes the cycle, providing the key to the solution. The remainder theorem reduces astronomical powers to single-digit arithmetic, providing a direct path to the solution without the need for polynomial expansion. Beyond pure algebra, word problems utilize operational frameworks known as highest common factor, or HCF, and least common multiple, or LCM. HCF is the framework for division and cutting problems, whereas LCM is used for problems involving meeting points or repetition. A specific formula binds these operations together. The HCF multiplied by the LCM is always equal to the product of the 2 original numbers. We can also determine the total factors of a number by applying prime factorization. Once the prime exponents are identified, we add 1 to each and multiply them together to find the total count of factors. Mapping the problem's requirements to these formulas allows for an immediate solution, bypassing the need for multi-step algebraic setups. Rapid inspection shortcuts serve as a final layer of efficiency during the exam. Numbers ending in 0 are always divisible by 10, 5, and 2. Furthermore, perfect squares and cubes are restricted by their final digits, which can only be 0, 1, 4, 5, 6, or 9. In banking exams, the approximation tactic is used to convert complex multiplication into manageable rounded figures. For example, 498 times 102 is simplified to 500 times 100, pointing to a result near 50,000. Revisit the problem from the opening, 3 to the 100th power divided by 7. Apply the modulo cycles and the remainder theorem logic. By identifying the cycle of 3 and mapping the exponent onto it, a seemingly impossible calculation is resolved in seconds. Success in these assessments relies on the consistent application of these mathematical algorithms. Practice pattern recognition daily to move past the limitations of brute force computation.